The paper delves into the structure of the symplectic Grassmannian SPG, 2n, as a variety, focusing on its invariant subvarieties and their connection to Coxeter matroids. By employing the moment map μ, the authors establish a correspondence between points in the symplectic Grassmannian and Coxeter matroids associated with the Weyl group BCN. This characterization is pivotal in providing a comprehensive description of rank 2 symplectic matroids that are representable over the complex numbers. The authors build upon existing knowledge of Grassmannians and matroids, particularly the theory of type A matroids of rank 2. They apply this theory to the symplectic Grassmannian, leveraging its status as a hyperplane section of the type A Grassmannian G, 2n. The authors demonstrate that every type A matroid is representable over an algebraically closed field of characteristic 0, which facilitates the characterization of the invariant subvarieties of SPG, 2n. The concept of thin Schubert cells is introduced, being invariant spaces closely related to the usual Schubert cells. It is shown that each thin Schubert cell in SPG, 2n, has a unique lifting to a thin Schubert cell in G, 2n. Consequently, the authors obtain a novel characterization of rank 2 symplectic matroids using a type A representative. The paper's primary findings include a characterization of the invariant varieties of the symplectic Grassmannian SPG, 2n, via a moduli of irreducible quotients associated to type A and type BC Coxeter matroids. The author's approach provides a deeper understanding of the geometry of the symplectic Grassmannian and its connections to matroid theory. The research concludes by emphasizing the significance of these findings in algebraic geometry and their potential applications in computer science. Symplectic Grassmannians, a class of algebraic varieties, are defined as the intersection of a Grassmannian with a hyperplane in the Plucker embedding, and are smooth complete intersections only for a specific value of the parameter k. The BCN group acts on rank 2 symplectic matroids, which possess properties such as the Witt extension theorem. The symplectic Grassmannian of isotropic lines is a homogeneous space and a linear section of the Grassmannian, with the Borel group and Schubert cells playing crucial roles in its structure. The dimension of the symplectic Grassmannian is given by the formula k, 2n k1, 2, and it is embedded in the Grassmannian G, k, 2n, as a subvariety. The symplectic Grassmannian is closely related to the GL2n group, with its geometry and algebraic structure influenced by the action of tori. The paper provides explicit equations for Schubert varieties in the symplectic case, and describes the t-fixed points of the symplectic Grassmannian as 2n, n1, points in the Plucker coordinates. A bijection between two sets of indices enables a more streamlined notation and analysis of symplectic Grassmannians, facilitating the definition of the set B, x, associated with a point x in the symplectic Grassmannian. The relationship between symplectic Grassmannians and classical Grassmannians is explored, highlighting shared generators for certain homology groups under specific conditions. The codimension of symplectic Grassmannians inside classical Grassmannians is also discussed, influencing their structure and properties. The paper discusses the concept of symplectic Grassmannians and their relation to rank 2 symplectic matroids, introducing the moment map μt and explaining its correspondence to a Coxeter matroid of rank 2. It also explores the properties of symplectic thin Schubert cells associated with BCN matroids, proving that the stabilizer of any element in the thin Schubert cell depends only on the BCN matroid. The paper then delves into the relationship between Coxeter matroids of type BCN and S2n, establishing a connection through a projection map π. It defines the degree of a matroid as the number of pairs, I, and discusses two operations of codimension 1 that can be performed on a matroid. The results presented contribute significantly to the advancement of symplectic geometry and matroid theory, offering new insights into the properties and behaviors of these geometric and combinatorial objects. The concept of symplectic Grassmannians and rank 2 symplectic matroids is introduced, with the symplectic projection of a matroid M defined as π m equals n asterisk operator b π m, where b, π, m are the admissible bases. The degree of M is the cardinality of A, M, where A, M equals I element of n. I comma I asterisk operator, element of b, m. The authors prove lemma 4.7, stating that if pi, m1, equals pi, m2, then there exists a matroid M such that pi, m, equals pi, m1, equals pi, m2, and m1 and m2 can be obtained from M by merging and splitting operations. This proof utilizes the octahedral Grassmann-Plucker relation to demonstrate that certain bases must appear in M2 if they appear in M1. The authors also consider the cases where A, M1, subset of A, M2, and A, M2, subset of A, M1, showing that M1 and M2 can be obtained from a common refinement by merging and splitting operations. Additionally, they consider the case where A, M2, A, M1, equals I, and A, M1, A, M2, equals J, and show that M1 and M2 can be obtained from a common refinement by merging and splitting operations. The concept of a maximal symplectic matroid polytope is defined, and theorem 4.8 is proved, stating that the symplectic thin Schubert cells are irreducible. This is achieved by showing that if pi-1 delta n has a member of degree at least 2, then it contains a maximal member, denoted by max n. The summary then moves on to discuss the decomposition of SPG 2n into a disjoint union of locally closed sets, and the existence of a unique matroid M that satisfies SPGN equals GM intersection H, highlighting its irreducibility. The main result, theorem 4.9, is explained, which discusses the representability of symplectic matroids of rank 2 over C. The concept of asymmetric lifting is defined, and an example illustrating this concept is provided. Page 16 is summarized next, focusing on the stability groups stab T, n, and stab T, m, their dimensions, and the exact sequence relating them. The lemma on lifting matroids is included, demonstrating how stab T, Mr., is a subgroup of stab T, Mo, with index at most 2. The summary concludes by explaining the conditions for Diog, lambda 1, lambda n, lambda minus 1n, lambda minus 1 1, to be in stab T, n, and stab T, m, using equations 4.7 and 4.6 as examples. The combined summary begins with the concept of symplectic Grassmannians and their relation to rank 2 symplectic matroids. It explains how equation 4.6 proves a specific condition for a matrix to belong to stab T, n. The discussion then shifts to assume A, M, and N with specific conditions, leading to the claim that Diog, lambda 1, lambda n asterisk operator, lambda 1 asterisk operator, element of stab T, n, if and only if equation 4.8 is satisfied. This, in turn, implies equation 4.9 and the lemma. The summary proceeds to corollary 4.13, stating that for any matroid n element of BC2n and any x, y element of SPGN, we have dim t. X equals dim ty, showing the action of ton SPG knees closed. It also covers corollary 4.14, which discusses the existence of an irreducible, universal geometric quotient SPGN equals SPGN, t. The discussion then delves into notation and definitions, including the concept of symplectic projections and their relation to representable symplectic matroids. It highlights the importance of understanding the set M2, BCN, C, of equivalence classes of representable BCN matroids of rank 2 and the CYC lemap. The example of a non-representable symplectic matroid is presented, raising questions about symplectic matroids that are not representable. The paper explores the connection between symplectic Grassmannians and rank 2 symplectic matroids, leveraging techniques from geometric invariant theory and algebraic geometry. It draws from foundational works in Coxeter matroids, Lagrangian Grassmannian codes, and symplectic standard tableaus. The authors utilize the language of matroid theory to provide a new perspective on the combinatorial geometry of symplectic Grassmannians. This approach offers a deeper understanding of the geometric and algebraic structures, as well as their relationships to other areas of mathematics. The paper presents detailed examples and proofs, illustrating the application of these concepts to specific cases. Future research directions include the study of higher-rank symplectic matroids and their connections to other geometric and algebraic objects. Overall, the paper contributes to the ongoing development of the intersection of geometry, algebra, and combinatorics, shedding light on the intricate relationships between symplectic Grassmannians and rank 2 symplectic matroids.